This is the documentation directory of our secure components repo. And yeah, I won't go a long time here because this stuff is probably better read on your own time. This isn't a nice digested slideshow like I've had past couple times because I'm it's not time for that yet on this stuff, but but I've made some interesting progress. So there's so I don't know if any of you have actually been over this yet, but if you start with just the overview, then I talk about in general the motivation for that and how what our goals are for secure components and what the top level types are. Of course, envelope is the star. You've heard me talk about that a lot. But of course, there's encrypted message, which we've defined elsewhere, and how we do private and public keys, seed-based digests, and SIDs. And we were calling these SCIDs, but that has a connotation that we're not really trying to promote here at this moment. It's a different application. This is not a self-certain identifier. Because as I thought about it, I realized we needed something that has less semantics to it, not more, which I've come to call the common identifier. And here's the document for that. Let me paste that into the chat here. And so basically the common identifier, I compare it to UIDs, URIs, digests, and the main goals of it were non-correlatability, neutral semantics, so it doesn't connote something that's permanent or something that's ephemeral because it could be used for either. Open generation, it basically means that as long as it's statistically random, it has statistically random bits and universal uniqueness. Those are the two core ideas of a SID. And then, of course, we're defining it to be 256 bits at this time. We could expand it later if it turns out to be necessary. And cryptographic suitability, which means it could be used as a component of, for example, a ratcheting key algorithm or something like that to generate further SIDs. So SIDs don't actually have to be generated randomly. They just have to appear random, and they have to be universally unique. That's the most important thing to keep in mind when you see me refer to SIDs. So the next thing I want to talk about is non-correlation. I just referred to that a moment ago. In that two SIDs, you shouldn't have to know whether they were created by the same ratcheting key algorithm or whether they were created by just random generation. You can't tell just by looking at them. They're non-correlatable. I want to avoid the impression in any part of this I'm a cryptographer. I'm not. I'm an engineer and creative technologist. And so if I say something that sounds naive, or if I start using terms that you're aware of have existence in the literature that I just haven't discovered, please let me know. I went looking for information on correlation and the various concepts around it. I didn't find a lot. So I invented some terms in this document. And if you are aware of better terms or pre-existing terms that apply, then I'd like to hear them. I start by talking about, if you're taking a hash, you start with an object which is called the image, and you make a projection of that using the hash algorithm. So, and then I introduce these concepts. So bit sequences are said to be correlatable if by examining them, there's a way to determine whether they are projections of the same image. If there's no practical way to learn whether a set of sequences are projections of common image, they're said to be non-correlatable. Then I realized, okay, well, there's a certain property I call quasi-correlatability. This is my term, and if nobody else ever uses it, I guess that's fine. But if it works, then let's talk about what it actually means. It basically means that you might have sequences that are statistically random, but might leak a size. So, for example, if I encrypt something, the output is the ciphertext is ideally randomly distributed, but its size is probably related to the actual input sequence, and it might be the same or might be larger by a certain increment or whatever. So the process of decorrelation.
I'm sorry, there are other kinds of quasi-correlatability. So for instance, there are certain signature algorithms where given enough copies of the signatures, you can then know that it's up at what algorithm it is. So that's another form of quasi-correlatability.
Right. So I introduced the concept of decorrelation, which is anything you might do to make things less correlatable as opposed to non-correlatable. Then I compare different things. So for example, signatures, as we're producing them, are non-correlatable because they use entropy. And so even if you produce different signatures of a single image, they're going to contain entirely different bit sequences. Now, as far as I know, we don't have that quasi-correlatability problem with the Schnorr signature algorithm. But again, I'm not a cryptographer, so I couldn't say for sure. And I can't even say what kind of risk that might present.
Not on.
Okay. Very good. So I point out that digests are the opposite. They are highly correlatable because two images produce the exact same digest. And that's a desirable thing most of the time, but not every time. So in that point, encrypted messages are quasi-correlatable because they're related in size to the image used to produce them. And I pointed out that, for example, SSKR shares, which are kind of a hybrid structure, are correlatable because while the actual core SSS output are just 16-bit, are just sequences of apparently random bits, we add a lot of metadata, which makes them correlatable. And then I discussed briefly what you'd have to do to make a non-correlatable SSK algorithm, what you'd give up in the process, unless you figure out a way around it. And then I discuss, how correlatable various kinds of, for example, specifically envelopes, because an envelope produces digests at every level. What is the various correlatability of various parts of envelopes? So I'm not going to spend a lot of time on that. And then I point out that secure components, I added a opt-in decorrelation on any element of an envelope. You can always say add salt, and it chooses the amount of salt to add, although you can tell it how much salt if you want. So for example, if you were decorrelating things by breaking them up into blocks and then adding a certain number of padding, so they're all equal size, and that hence decorrelating them, you could choose the amount of salt you want. But by default, it adds an amount that's between 8 and 16 bytes, or between 5 and 25% of the object to help reduce. And if you add salt to anything, it becomes decorrelated, even if it's a simple like integer 1, that would always produce the same digest. But if you call add salt, you're basically guaranteeing that same envelope, whether it's a subject or predicate object or whatever, will never be the same as any other thing from its digest point of view. So if you salt it and then redact it, it's basically like a salted password, a hash and salted password at that point. So then I point out how you create a simple envelope, and then how you could add salt, create that using salt at every level. So that if you redact any part of this envelope, so this is again the subject, becomes the predicate, this is the object. So, but notice that they're all envelopes themselves. So they all have assertions on them which contain salt, and so that's how you'd opt into decorrelation as you create envelopes here if you care about it. And again, my goal is that if you don't need this stuff, you can ignore it, and if you do need it, it's there. So and that would be the idea of progressive discovery, in a UI design, and that's how I'm trying to design envelope. Okay, so with that said, another major thing we've talked about is redaction. As I thought about this, I realized that redaction is one use case of what I'm calling elision, which is a more general concept. So to elide means to leave out, to redact means to hold back. So there's many reasons why several reasons at least, why you might want to elide something. Redaction is one of those reasons that you're consciously holding back information, and so basically I introduced the idea of data minimization, selective disclosure. So for example, if a government issues, this is again envelope notation here. So here's like a driver's license. This is a SID, which represents my unique identifier with the government agency, the issuing agency, or maybe I provide the SID and they give me this document based on it. It doesn't matter. But the point is, this is 32 bytes of apparently random data that is unique to me. And so I have my first name, last name, and several other data here, including CBAR, an embedded photo. And then this whole envelope has been signed by the issuing entity. I can't change any of these without invalidating the signature because of the Merkle tree. I could redact these things, however, because redaction, or in this case, elision, doesn't actually change the whole Merkle tree. So if I just wanted to reveal my birth date in my photo, just so somebody could verify my age, then I could elide everything else and the signature would still verify. So this would be a case where I would elide everything but what I wanted to reveal. And it still maintains the Merkle tree without revealing anything else except the macro structure of the object. And so then there's, as I mentioned, the term elide means to leave out, let's see. Yeah, so the difference between elision and redaction is not functional but semantic. Elision is what is accomplished, while redaction is one purpose that data might be elided. When one redacts, one is choosing to withhold information with no affordance or expectation that the receiving party can or will recover it. But there's another common use case for elision, which is referencing. In this case, information is elided with every affordance and expectation that the receiving party can and might choose to recover the elided information. And so I'll go into the scenario where it's the same document as before, but whoever created this document before it was signed added a dereferenceable via assertion, which basically says that if you have the digest of this, you can use that to an IPFS to retrieve the actual data that would go here, that would fill in this slot. And because this is actually an assertion on the object, it's not an assertion on the predicate. It's not an assertion on the assertion as a whole, which you can do. It's just an assertion on the object. It basically says this object can be dereferenced via IPFS. This could be a URL or other things. We haven't defined a standard for how that would work yet, but the idea is this is possible, and we see use cases for this. So in this case, the photo hasn't been redacted; it has been referenced. In either case, it's been elided. So these are both the use cases of elision. So because there's an affordance to recover at present, and because envelope supports a number of Merkle tree preserving actions, the actual photo data can be retrieved using the digest, and the credential can be transformed to its dereferenced version while still preserving the signature. And so this is the actual CBOR now that's been retrieved that fills in that slot but doesn't change the Merkle tree. So if I wanted to fully redact my photo, I would just elide the entire assertion. And again, you identify things by their digest. You can then say to secure components, elide anything with this digest, and you get back an envelope that has the same Merkle tree, but parts of it are elided. So I point out that whenever you create a digest of something, you've basically created an immutable reference to that object, and you can have various kinds of registries and so on where you can give it a digest and it will hand you back the single possible object that could meet that. Because unlike a generic binary file, which is treated as a simple sequence of bits for the purposes of Computer's digest, an envelope is treated as a tree of objects, each of which produces a digest and which may be selectively elided without affecting the digest upwards toward the root. So this means that a digest referent is immutable. Let's see. And it's important to realize that while information may be elided in an envelope, no underlying information that went into its creation can have been mutated, added, removed, or altered without invalidating the Merkle tree. And any elided document can still be transformed to the unelided version if the elided parts could be retrieved. And also one thing you could do is, if I mentioned in this section, this document is a work in progress. It's going to end quickly here, and I'm still working on this. So expect in the next 24 hours to have even more information here. So sometimes you don't want immutable references. You want what I call mutable references, which means that what is retrieved from that reference could be different depending on who you retrieved it from, when it was retrieved. And we're all used to numbers like driver's license numbers, which different government agencies may have different information on you based on that one key or that one number. So for this is the purpose of SIDS, that it's a universal way of identifying mutable objects and relative to envelope, the use of SIDS is optional. So again, we're trying to create like a Lego system here where if you don't want to use SIDS, you can use some other key. That's fine. You can use it. But SIDS are there as kind of a universal thing that has certain properties to it. Mutability occurs when dereferencing identifier might return a different set of information over time, or depending on the common identifier. That's not good grammar. I need to edit that. So anyway, then I go on to talk about how you perform elision, and I point out how you create a target set of hashes of digests in the tree, and then you basically say either hide everything matching this digest and everything below it in the tree, or keep everything but or reveal only what's in the target. And this is kind of where it starts to peter out here. So, this will have a lot more examples in it, so you can understand how this relates to it. But yeah, so that's basically the where I've been going with this, and this will be much more filled out in the next 24 hours or so. But let me make sure you have the link to this stuff. And yeah, I'd love to hear some questions or some ideas. But I think it's again, the idea is simple things should be simple and complex things should be possible. And so that's the value I'm striving for here. Again, if these kinds of use cases don't apply to you, you can ignore them and just use it for encryption, or just use it for structure, or use it for all kinds of things. One other thing I did want to show you is the where is it? Here. So this is using envelopes for requests and responses, which is definitely germane here. So this is the structure I have for requests and responses. If you look at the actual secure components thing, I have an example of what's called envelope notation. This is basically how, envelope expressions, and so on. Envelope expressions is ways that you can use the envelope structure to enclose evaluatable expressions like add two numbers. It's just a trivial kind of example here, but then how you would notate with using CBOR tags, functions, parameters, composing functions, logical predicates, and so on. It gets more and more complex because, again, you may never need this, but this is, I wanted to make sure that this structure is capable of these things. So what you see here is a request ID, which is a SID. It's the SID that's been tagged as a request, so you can immediately recognize it as a request. You don't know how the SID is generated. You just know it has the properties of universal uniqueness and statistical randomness. The body of this is a function call. This is just a CBOR tag, and it's got one parameter, the seed digest. So you want to retrieve a seed. You're giving the seed digest the seed you want to retrieve. And then this is the body of the request. This is all you need to do to process the request. But here's an optional note assertion. We had bespoke CBOR structures for this, but we've recast this into the structure of envelopes to make it more flexible. For example, you could add another assertion with vendor specific data, and other people can read this and not know anything about it. And if they know about it, then they can, and you publish the specs, then they can parse it and do it. So there's no limit to how you can add things here. And then the response is just the same CID tagged response, and then an assertion, which is the result, and the seed, which is a crypto seed. We've written that up elsewhere. So this is how you'd request a key or a derivation. This is how you'd request a PSPT signing. This is how you request an output descriptor response. And these are all currently working in Seed Tool and Coordinator, which are available in test flight right now. So, and again, this is one of, I hope you'll see many applications of the envelope structure as a way of moving data around in very flexible ways and transforming it. Okay, that's what I have. Questions?
Yeah. So I did want to share a little bit of the motivation and design requirements that we had for Wolf. One of which was, some long concerns that we've had with DIDs over time. I mean, I'm one of the co-authors, and I'm very proud of our work there. But somewhere along the way, we lost a lot of the privacy aspects of things. They became fairly correlatable in a lot of their actual implementations, and in fact, many the most popular implementation right now is DID Web, which isn't even decentralized. So we wanted to basically have something that allowed for a little more depth in the sort of censorship resistance and privacy and anti-correlation aspects of these things, without necessarily diving into deep zero knowledge proofs and other different types of things where we're using some fairly basic mechanisms, and it has some limitations. There's some things that it can't do, but I believe that design is such, especially with crypto envelope, that we can add those things that we want it to do. There's no reason why you can't use a BBS plus signature in here with zero knowledge. Yeah,
I want to emphasize that all the choices that Christopher described are not. First of all, now is a good time to change them if we really wanted to, but there's no reason why we can't add support for more later, because we're dealing with CBOR. Everything is tagged, so everything basically has an identity, and if it's not tagged, then it has a default identity from the spec, so it doesn't take up extra space when. But we're future-proof because we can always add something else later, encode it with a new tag, and then structures that software that recognizes the structures can just go ahead and use it while remaining completely backward compatible.
Another fundamental principle was this idea of, progressive trust, where, all you may need to know is, all you're embed to know is that, there is a persistent party on the other end until you've identified yourself. So the next step is it, embeds in its crypto response a crypto request for, some authentication information from you. And that, and that maybe then serves as a, trust on first use set of keys and a CID that is unique just to the two of you, that allows you to interact with each other until you need more trust. And now you need a bank because now, you're doing a loan or something of that nature. But you don't, we don't want to require you to have to do every bit of authentication. There are various doors you can knock on that will open depending on, your specific requirements. And, obviously we want this all to be designable so that, it can leverage ratchets and other different types of mechanisms that allow for additional privacy and security over time. So we're running a bit late, but any kind of, does this feel like, I haven't heard anybody who says I have to have this right now, but is this adding too much complexity for, do you feel like us thinking about this type of stuff and beginning to, to architect it and code it is going to pay off?
So for us, personally, proxy, I think, sorry, go ahead, Ken.
That's very good.
Yeah, I was going to say, I think for the context of this particular group as it relates to seed recovery and maybe collaborative key management, that may be too much complexity, but for me, from a proxy perspective, this is very interesting because it's addressing a lot of the problems that we've been designing around and solving as well. So there's a lot of similar directions that to what we've implemented for other use cases. So it's interesting from that perspective, and I'd like to see further further how it goes.
For me, I feel like it's actually really simple at its base, and it's really like it's like selectively revealing the complexity as you need it.
Yeah.
And I really like that about it. Like, honestly, looking through this, I'm just like, my brain's kind of spinning like, this seems like something really cool we could use for a lot of different things. Like, what are those things? I'm not sure yet, but I think it's really, really cool. Like, just to speak a bit to the mutable references, like, I assume then that the SID is the part that participates in the Merkle tree to keep everything from changing when the mutable value changes.
So by mutable, what I mean is that, if I have a number, a SID, for example, and I ask Simon what he associates with that SID, I might get back a set of assertions. If I ask you what you associate with the SID, I might get back a different set of assertions. Or I ask Simon a year from now what he associates with that SID, I might get back a different set of assertions. So you can think of it as, say, a primary key in a database where the other records associated with that primary key might change over time, but that primary key doesn't change. Now, once I get back a structure that, say, is a SID with a tagged set of assertion or with a set of assertions, that structure itself will have a digest. Every part of it has a digest, but at the top of the root of the Merkle tree, there's a digest. So if I want to snapshot that and store that in, say, a content addressable storage system or something like that, I can take that top level digest and then basically, or anywhere that envelope occurs inside any other envelope, because it's all recursive, I can replace it with that digest. Now I'm no longer using a mutable digest, I'm using an immutable digest, or an immutable reference, I meant. So yeah, just think of SIDs as basically just, a primary key for something that can change. And digest as basically just a hash in a content addressable storage system.
But if you were to replace that, though, then you're changing the upper parts, so you have to update the rest of the Merkle tree, right? So,
yeah. So, for example, as I'm developing, for example, my actual code that you use to construct envelopes, every envelope you create is an immutable object. So you don't say add. You say add an assertion, but what it does is it creates a new envelope with that assertion.
Mm-hmm.
And if you compare the root level digests to both envelopes, they're different now. So every time you change anything interior, you change that. However, then you can take that object, embed it in a larger object, and that will, of course, change the larger object's root hash. So, but there's a certain number of transformations you can do that, for example, to encrypt or decrypt a subject, to elide or unelide a subject, things like that, that don't change the actual macro digest structure of the envelope.
Or let you know what changes, what the differences are. And this becomes, there was a big name change that happened in the last couple of weeks because there is a subset of SIDs, which are SCIDs, which are self-certifying identifiers. So those have additional cryptographic properties, but they should be undistinguishable. So, you know, a SID in the most of these cases, let's say it's unique session ID. You don't need to know how that session ID was created, whether or not it was a PDKF function or some kind of key derivation. All you care about for request is that when you respond to a request, your response needs to use the same CID. We're trying to keep that very things, but some things do require SCIDs, which are self-certifying identifiers, where we basically have some kind of root state that is being set. You know, for instance, you could have a SCID that is public private key set, but that only signs an assertion that is used to initiate the hashes that say in the future use these other keys or use these other children keys or whatever. So now you can do something that's very DID like, where somebody can basically in effect own a random number and prove ownership of that random number. And then from there, you can extend to other different types of stuff and get it certified and have other people do web of trust things there. So there's definitely the intent is there that we move more into the DID territory with this, especially the blockchain-less version of DID. And there's, if you want to see a little bit more about SCIDs in general, we're borrowing a lot of ideas from Keri, spelled K-E-R-I, DIDs, which are also self-certifying, but ours are designed to, do interesting things like, you and I can enter into a, not a frost, a MUSIG operation. So if you and I enter into a MUSIG, at the end of that MUSIG, you and I have a joint secret that only operates when you and I do an operation with it. But the public key is unique to both of us. In that way, it's a lot like a Diffie-Hellman key. But the difference is that we can also use that same thing for a MUSIG of all 7 of us. And that basically now becomes an identifier for the 7 of us, where it requires the key material for all of us to participate. And so there's some really interesting things when we start talking about Schnorr and quorums and Frost and MUSIG, et cetera, with CIDs that allow
a
lot of power.
Yeah, let me point out one other thing, because I noticed that when I started dipping into the whole DID space and looked at JSON-LD and so on, the whole normalization issue was a huge issue, and how you go about doing that. And basically, I've baked that into Envelope from the start, because I specify that you're using deterministic CBOR, which is a specification for how you encode things in CBOR. So, for example, if you're encoding a CBOR map, the keys have to be sorted. So you can't just if you have a key, you have to have it has to appear in a certain relationship to the other keys, things like that. So, given that there's only one way to encode a CBOR structure, and given that, for example, the assertions on the subject in an envelope are sorted by digest, and you can't have a duplicate assertion. If you and I assemble an envelope, in different parts of the globe, as long as we're using the same parts, it doesn't matter the order we assemble them in, you'll get the same envelope with the same digest. So I think that actually opens up some really interesting possibilities. But it basically means, if it's a specific envelope, there's only one way there's only one conclusion you can reach by assembling its parts, which is that envelope. So you don't have to normalize the envelope once you've assembled it. It's already normalized. It's normalized as you build it.
We've also designed it, although there's still more work to do, that you'll be able to do things like merges. So just in very similar data replication technology, but sort of the next generation that Git uses. So you'd basically be able to have 2 different CBOR objects where a lot of the values are the same, and the parties that are involved in that object, in that object, who have, you know, authorization to update it in the skids, can merge those two objects. So we're trying to be friendly for things like the future of Git and other. Wolf, what's the name of the specific? We were looking through the data replication, sort of the IPFS type of
I'm trying to remember. You're talking about content addressable storage or something like that, or
no, the particular that brings the state all into alignment in distributed state. There's a particular
you're talking right, yeah, right. You're talking about immutable architecture in general. There's a book called The Art of Immutable Architecture, which I'm quite inspired by. That I also want to make sure that envelope suits the needs of. That basically, once you have the idea being that you can have eventually consistent systems where you have, which are distributed systems that may maintain their own state, but they're exchanging state, and as they do, they all converge on one state, no matter what the order of operations. And that's very useful when you have things that are only sometimes connected, like, you know, mobile devices and so on. It's definitely things that, for example, Apple uses behind the scenes a lot in iCloud. You know, a lot of developers use it, for example, like HackMD, you know, uses various kinds of techniques to make sure that as several people are typing, that those changes, when they finally arrive, are all reconciled correctly. And that's the whole idea of eventually consistent systems. And so I want to make sure that envelope is also a good building block for systems like that.
I mean, they aren't quite the same as solution as blockchains. They don't they don't necessarily you know, guarantee that consistency can always happen. And you know, they're not Byzantine tolerant, but they're very powerful, and especially in cooperative systems. You know, we want to be able to support those types of structures, and we've got that in the design.
Yep.
Wolf, do you know if HackMD uses CRDTs under the hood?
I do not know if they use CRDTs. I haven't actually looked into directly their architecture, but certainly any system like that allows real-time collaboration has to avoid locking. And to do that, you basically have to have something that is convergent like that. CRDT stands for conflict-free replicated data types, and that's a core of eventually consistent systems.
Anyhow, lots of different domain knowledge, different skills, etc. And you know, one of our key things is, although these are, I think, you know, well specified in some advanced different topics, we really want to be open for people who have a, you know, specific domain. Okay, well, gosh, if you only supported X, that would just solve so many different problems in this other domain that we're not as much an expert on. That would be great.
Yeah, this is definitely a work in progress. But if you like, for example, Ken, you know, you sounded like you might be a bit inspired by it. If you look into it and you say, you know, well, how would this work? Or, you know, can it do this and so on? Please strike up that conversation with me. I really want to have it, because
for sure.
in some cases I've thought through scenarios is like, oh yeah, you need to actually implement any specific affordance for that, because it kind of falls out of the decisions I've made. Other times I've realized, okay, for, you know, this or that purpose, you know, we should at least have a standard way of doing this kind of thing, and so I should document that. But yeah, it is really, you know, I really appreciate what you said, Ken, that, you know, yeah, it's simple. And that was my original name for envelope was simplex, because it was a simple container for complex ideas. And we decided envelope was more marketable, but yeah, that is the goal.
Yeah, I think, not that I have any in mind yet, but like, I think it's often, when things are simple like this, it's often helpful to do sort of a cookbook style, like to show some of the stuff that's possible, even if you don't mention it explicitly, because people may not think about, you know, the simple things they can do with it.
Well, the cookbook is my unit tests. If you go through the Swift unit tests in the testing folder, the test folders, you'll see I'm doing all kinds of things and double checking to make sure everything, you know, does round trip encoding correctly, and the simple cases are you know, very few lines of code, and the complex cases aren't hellish to achieve. So most of my unit tests files, if you read them from top to bottom, they have the simpler tests at the top and the more complex stuff at the bottom.
Yeah. And we've definitely got a lot of things. So, I mean, the current plan right now is obviously for Wolf to finish up closing the hood on some of these docs in case some of you want to actually dig into it. We are going to do a crypto version of it with these choices in Swift, because it, since he's already got all this stuff in Swift for testing purposes, adding the CLI to it is pretty straightforward. And that will then allow us to, have better prototyping capability and exploring, you can do it all for all these operations from the command line and take a look at them and try them out and go, oh, but how do I do X? And we can do that. And while we're having some security reviews on it, make sure that, our salting operation actually does what we promise, or that there isn't a weird signature malleability problem that we have to deal with, or somebody basically says, why don't you use VRFs for this? It's so much better. And we go, oh, well, we need to add that to our crypto suite because they are better. That type of thing. Okay, well, we're on the hour, so we've been at this for 2 hours. Thank you very much. 2 weeks again. That makes sense for everybody?